vertical you get,
Yeah, it goes
the more,
right up.
the more it's going to not reflect
That's right.
at a higher frequency.
You're right. It goes through.
Okay.
That's why
So
it works up to 40 meters.
what I wanted to show you is different point about NVIS. You are the elevation angle. I prefer I repeat, I don't like takeoff angle, because takeoff is bringing to think that we are transmitting, but
Yeah,
we are
okay.
also receiving.
Yeah, okay.
And I prefer to make my reasonment with incoming signal than going out signals. So that they say elevation, okay. So you can. What is interesting? It's a statistic for West Coast, but it's same for us. You can see that the distance and the evolution of takeoff angle. So for a very close, about 100 kilometers, you see that it's very high, because 80 degrees is close to the vertical. Okay. So in this case, the signal are really coming from the sky, and you can see how it's the evolution of this angle with the distance.
It's all how it reflects, eh?
Yes, it's a reflect.
C'est ça qui gouverne tout.
Yes, exactly. It's geometrical.
Just assuming a certain F2 height or something, or
To hide.
F2 layer height.
I think yes, of course there is the layer. It's related to the layer 8 and the geometry after that. But the layer is not always constant, because it's not always the
No,
same
I
one.
know, exactly.
Okay,
Which
so
is
it's a statistical
reflecting,
thing.
and
Just
it
an average.
depends on the MUF, the maximum
Yeah.
usable frequency. But as you see, is another value, some value that I got from forum. The guys on 160 meter was giving those values. You see, so you can see that even at 160 kilometers, 1,600 kilometers, we even on 160 we are low. We are starting to be low on the angles. That's a very interesting graph took in the RRL antenna book. You have the comparison of different antennas with the takeoff. It's a HFTA like graph, okay? And you have the gain of the antenna there. And it's interesting to compare all those antennas together in an NVIS consideration on 40 meter. And you can see obviously that the best antenna for the DX have a big notch here, and that the very low antenna, use a 2 feet dipole is very low, is never better than it, except there it's the same. What I have done on this graph, I have added the distance. Okay, that's more interesting, because the angles by themselves don't speak. You can see that what is interesting us is the low distance. You can see that even finally the very high dipole is not so bad. And that especially if you take a 10 feet dipole, it is not on the short distance. I think the 3 meter high dipole is not very good compared to not only the 100 feet, but which is quite high, but 66 feet dipole is not very high. It is a normal height for such a dipole. It's the same. So actually, that I'm not convinced by the fact that the NVIS is a real an advantage. When I see that, you see, except for this antenna, where we can say there is a noise problem, because we will get much QRM and there is a big notch, but most of the high correctly high antenna are good also for short distance. So I think that the NVIS concept is not that very interesting by itself. I think that the people speaking of envies is just because they have not the possibility to put a higher antenna.
Well, the point is, if you're trying to deploy something for
Exactly.
communication,
Fast.
then it's not a matter of saying how much better it is. It's just, at least it works well for
Yes.
that purpose.
I'm
Even if
okay, but what you were saying is that when we say envies, again, is it
Is it
a
optimized
need
for that?
to give a name to that? You see what I
Yeah,
mean?
I understand.
Actually, that means that any antenna is good for short distance. But
I'm surprised it's not named after a call sign.
that's my thoughts.
NV1S.
What giving a name?
Exactly.
Why giving a name to that?
It's not NV. It's not NV1S. Then.
Yes.
Hey, we wanna.
Okay, that's my conclusion about NVIS antenna. That's again a concept for nothing. According to me, okay, it's my opinion. But of course, that means that whatever the piece of wire you put on everywhere on the ground, it will work for emergency communications.
If I want to call my antenna that's only,
It's very easy
well,
to
I
put
only
a
time I
flagpole
get off the
with
ground
2 feet.
NV, I'll call it that.
I know the military uses NVIS, especially with their mobile operations and stuff like that, and it's it's a limit to a few hundreds of kilometers or so with their HF communications, and that's what they need. They don't need DX.
They purposely do not want DX.
They perfect, but they wanna listen to me.
Oh, I have a problem. I cannot get out of my PT.
Your PowerPoint.
You can press escape.
Escape.
So perhaps that? Okay. So, now I just remind you a PowerPoint that I've already shown you. Just to, we are speaking now about receiving antenna. So I'm coming back to that. You remember this antenna is a pattern that is real, that I have simulated. And remember that we were working with an antenna with the wanted signal there and the equal signal, not wanted signal, a QRM, a noise there. So if the gain is minus 10 dB and here it's minus 4 dB. So if the signal has the same strength, they are very close together. If I turn my antenna, I improve putting my antenna in a different direction from the receiving direction. I have an amelioration of my signal loss ratio because the losses there are less than the losses there. And I can even make a very strange thing, is to put the antenna in a totally wrong direction, but actually, as I totally notch the noise, I still have a better reception now.
At the end, if you hear it, it works.
Yes, exactly.
Yeah.
Unless there's somebody else not quite as strong
Yes, of
over
course.
there.
But
An American with a kilowatt,
what this
Rank
thing
doing.
is meaning
actually,
is
1K
that
above you.
the reception concern is not at all the same as the transmission concern. And that's why we can see that the need of special antenna for receiving. Okay? That's all. That's just the goal of this PowerPoint. And so now we will simulate. No, I will first. I want to show you another PowerPoint. Sorry, no, sorry, that's the wrong one. Okay, I found it. Okay. So, as you can see, we cannot use the same criteria for transmission and reception. So, people have tried to define some way to measure the quality of a receiving antenna. Currently, in the amateur community, we are speaking about it's a, you know, the front to back ratio is not a good ratio because we don't know at which angle, we don't show. You remember that if the pattern of antenna is something like that, okay, what is the front to back? Is it that to that? Is it that to that? Is it, so it's very difficult to define a real front to back. So the amateurs have decided to use two, what we should say not ratio but merit figure. The first one is the NDF, directivity merit factor. Why this name? It's a name. It's a ratio between a gain in one-tenth direction and averaging of gain in the back half sphere. You see what that means?
Yeah, the
You
whole
take the
thing.
whole half rear sphere, you calculate the average
Yeah.
value of the gain there. It's not obvious because you have, you know, as the angle are varying, you cannot put the same weight on every place because actually you have to take some array, not angle, but some array in the sphere. But it's not very difficult to do.
So you weight it, I mean, the stuff that's coming out of the ground, maybe you don't care about it. Unless
No.
you've got some very noisy.
No, but what I mean by weight is actually is the, you know, when you do something like that, you cannot, the sphere here, you see, it's difficult, but the piece of
Here-
the
here
piece
we
solid
here
angle.
is not the same array that here, which is much larger.
Oh,
So you
okay.
cannot say, oh, I take the 90 degrees and I multiply. No, you have to divide by the array there.
Well, that's, yeah,
So
okay,
the weight
yeah.
is not a real weight. It's just the total array of the sphere.
Area, you mean?
Yes,
Okay.
the area. Because this, I don't go.
You have to
go
do
into
it.
side, but I've written that the algorithm and you have to take care of the real array of each value that given by the simulation. Just
Okay.
so, but the idea you get a big amount of values. You take an average value and you compare it to the wanted direction value. Okay, there is an that's an illustration that a receiving antenna pattern with different different phase, because it's end fire. Actually, you have two. In this case, you have two vertical antennas for reception, and you have a phase between the two antennas, and the phase is 90 degree, 105, 120, 135, and that give you different ratio.
The phase is the in time.
No,
Time difference.
yes, the phase.
Oh, okay.
Okay.
Relative to frequency.
Yes,
Yeah.
it's a lag.
Like, okay.
Okay, so and it's expressed in degrees.
Right.
So that just to show you that, that there is a, you can see that, for example, here it's the best antenna 135. It's that one. Well, obviously we can see that here also.
Mm-hmm.
Here. Okay. So obviously there is less noise coming from the back. Okay.
Right.
So there is another one which, instead of the half sphere, it took the total sphere. I prefer that one actually, because I don't know why just the rear is a problem. Everywhere is a problem. So there is of course double that the number of values, and then you have another example there with this time two in phase, two vertical in phase, but with a distance between them. That's the spacing between the antennas on 160 meter, I think. And so you can see at the same time that there is different attenuation from the side. This time the antenna has no rear front to back because it's symmetrical, and this time the noise is attenuated from the side. That shows that the two ratios can be used according to what you want to measure or what you want to optimize on your antenna. Okay, so I will not stay much time on that, but that's what is used today to compare receiving antenna. Okay, here you have some idea of what we can do. We come back on receiving antenna, but that's to give you some ideas of what we can have as numbers. Okay, even if I'm not okay with that, because I think that there are two. No, because in the same distance, the wanted direction is a problem. And in this case, I don't know why they made this table with wanted direction of 20 degrees.
Mm.
So that's a bad idea, because actually, always the same, even if you take the half sphere, okay, you have to take the direction of angle of interest, which are mostly under 10 degrees.
You mean
In this
elevation
case, I
angle.
don't know why it's at 10 degrees, at 20 degrees.
Elevation angle, you mean.
Yes, and that's not a good idea, yes. So, but let's give an idea of what we can expect. So, a simple beverage, we will come back soon on the beverage. A short beverage on 160 meter, it's a half-wing beverage, is those numbers. And on the other thing, you can do the 160, so a full-length beverage with four, actually that's four beverages. You have two beverages like that, you know, with a leg, and another two. So you are at the same time you have broadside and the end fire. So there are four beverages in parallel, and you can have a very elevated
You mean
number
broadside receiving
Yes.
this way.
there. Yes, broadside they are parallel, and end fire they are
Yeah.
they are one behind the other. So the people are doing that. They are taking four beverages. They are putting two at 5 meter distance for the end fire, and there are two set of end fire 90 meters apart.
End fire that way, off the end.
Yes, end fire
Yes.
and broadside. Broadside by 90 meters and end fire just 5 meters, but this distance is usually 20 meters. You understand?
Yes.
I know I'm fast, but that's not the
You need.
You mean it receives
What I
broadside
understand
signals?
from that is that you need a lot of space to.
Yes, exactly.
Yeah,
Exactly what
it's
you
impractical.
All is
Huh?
point.
It's
Broadside
impractical
array.
for
For you,
99% of the
It's why
population.
it's why I don't
For your
spend much
neighbor's
time on
backyard.
that. I just
Okay,
say
I
you
understand.
why we got those numbers.
It's not receiving broadside. It's just placed broadside. C'est placé broadside. Ça reçoit jamais broadside in beverage.
No, mais whatever what means broadside, they call broadside
Okay.
the fact to put two antennas,
Next to each other.
okay, next to each other, perpendicular to the direction.
Understood.
Instead of one behind
Okay,
the
because
other.
that confused me.
Don't try to understand what means broadside and fire.
Okay.
I was never able to understand.
Okay.
Just what I did is broadside is there are side by side,
Side by side direction.
and
Okay.
fire there are one behind.
When
Je
you're talking
comprends.
about a
Je
dipole
comprends.
array,
Okay.
when a vertical array, it's where it's receiving.
Okay, I understand, Gilles.
What does 3 dB angle mean?
That's the open. It's
Oh, that's
exactly.
okay. The width. Okay. The
Okay, exactly.
I got it, I
For the
understand.
antenna, you know that's
Yeah,
for
yeah.
that, and here you
3
stop
dB.
at
the
3
beam width.
at
so to
3
speak.
dBs.
Yeah. Okay.
Beam width.
So it's not really a beam, but
That
beam
let's
width.
show the wideness of
Of the main lobe.
horizontal. Yes. Okay. So another set of values is for some other antenna. The previous one was with beverage, and that one with verticals. It's just to show you what we can see and the values. We will
Look
not
at those
develop
numbers.
that because it's not practical for you.
Look at those numbers.
Hmm?
Yeah, look at those numbers. 25 DMF.
Yes, that's very
21.
impressive. Because 1 dB of DMS is much. Because that means that you are
It's hard to rotate.
You know, 1 dB
Tu
of
dois
DMS
vivre sur une
you are
ferme.
activating everything
Yeah.
with 1 dB. That's much.
Gotta live on a farm.
Okay, so we will take a pause now, okay, cinnamon, and we continue with some simulation of receiving antennas.
Perfect. Thank you.